Okay. I promise I'll get them back to you, but unfortunately I have to wait until the makeups are given and then keys and all that fun stuff gets posted. Meanwhile, I want to pick up with our t-test, sorry, our t-confidence intervals with smaller sample size, or where we don't know our population standard deviation. That's why we're using the sample standard deviation in its stead. So, I said earlier, working with these functions to get our t-values is going to suck. And because I need my degrees of freedom, finding this t-value is easier done with a lookup. Again, in the back of our textbook, we've got a table. Our t-value is always returned as the positive value in this table. And notice, here are our confidence levels. So if I know how confident I want to be, then I know my degrees of freedom. I can look up the appropriate t-value. So if I'm working with this class, there are 18 of you. If I consider you the population of this course, I'll have to use a t. But if I consider you a sample of the statistics students I will teach, then my degrees of freedom is 17. And if I want to be 80% confident of my answer, or 90% confident, or 95, or 98, or 99, I can use this set of information to find them. On the other hand, I would point out to you that once we get to relatively larger sample sizes, this table isn't going in individual numbers anymore. We're jumping by fives over here. If I have a group of 63, I'm better off to round down to 60 if I need to use this table. But I can look up these t-values in Excel directly. In Excel, the command to return a t-value is t.inverse.2t. 2t, what's 2t mean here? Two tails. Because I'm thinking about being inside a region, I'm thinking about the left end and the right end as being the bad parts. So I split the bad area into two pieces. And that's also why, if you notice, in our table here in the headers, that 95% confidence goes with a 5% on two tails and goes with 0.025, the alpha over 2 that's being used in that symbol. And that's because 2.5% is in the bottom and 2.5% is in the top. 5% total on the outside. Now, I actually need to give this two arguments. This command gets alpha, not alpha over 2, it gets alpha. So if I want to be 95% confidence, I'm going to put 0.05 there, and then I give it the degrees of freedom. So, if I tell you that I have a sample of size 10, then my degrees of freedom are 9. If my degrees of freedom is 9, I need to look up the t-value for a 95% confidence interval. If you've got your tech in front of you, jump into Excel. By the way, I believe this command also works in Google Sheets. Not 100% sure it's the same format, but I believe it is. If you've got a graphing calculator in front of you, the same thing works. There is a t inverse in our distributions. Now, I'm again going to have to tell it the area I want to cover. Oh, wait a second. You have left, right, center on this one also? Okay, good. Yeah, that's the wrong one. Here's a case where I'm going to look at the picture on my table again. That's the wrong number. I promise I'll tell you why it's the wrong number in a second. Look at this table. Look at this picture. What's this picture show me that's different than the picture I described earlier?
This is only ending 95%, not only the bit of 95.
This is only showing one tail, isn't it? And I talked about splitting it into two tails. So when I told the calculator to use 95%, it's including the tail on the left. It means I'm not getting the right value. If I want a 95% on the calculator, I'm going to have to give it 975. How do I know that's the right answer? Degrees of freedom 9, 95%, 2.262. And that's also how I knew this one was the wrong answer, because it's giving me a 5% size tail as opposed to a 2.5% size tail. It's giving me one tail, not two. Stupid picture. The calculator's dumb. If I had a left, right, center, I could tell it's center, but I don't have that on the option. So it does left by default. In Excel, I can give it 0.05 because that's the area in both tails, and the command says 2t. So I know it's using both tails. It'll split that in half and do the 5% on each side, 2.5 on each side. So the Excel is smarter than my calculator here. But that's why this command is the one I want to use for doing a t inverse. I don't just want to use one tail, I want to use two. Questions? Let me expand on this problem. If I tell you for this same problem that I have an average of 270 and a standard deviation of 20, I want a 95% confidence interval. Well, now you can give me that. That's where I use this formula to get the edges of that interval. So my margin of error is going to be 2.262, that's the t-value, times S over the square root of I'm being sneaky here.
Would be 10, would be square
root of 10. I didn't tell you how many people were in the sample, did I? That's n, but degrees of freedom is n minus 1. So knowing that gives me n. And now I can multiply all this out, and I get 270 plus or minus, what is that number? Let's go with 3 decimal places there. Hold on, Leah. What you got?
got 14.306.
And then I'll add and subtract that from 270 to get the edges of my interval. So I did my sample, and I got an answer for an average of 270. I am 95% certain that the real population average is between 255.694 and 284.306. 95% certain that's the section of the x-axis I want to be precise. Questions? If I actually do have just the pile of data, problem 25 here. A random sample of monthly rent paid by 12 college seniors living off campus gave the results below in dollars. Find a 99% confidence interval for the population average, assuming the sample is from a normal population. That assumption is important. There are no weird outliers. There's nothing oddball about that. This is a small sample, though. There are only a dozen people in it. But that means what I need is I need the average. I need the sample standard deviation. And then I need to calculate my t-value based on degrees of freedom being my population is 12. So my degrees of freedom is 1 less, 11. So again, if I have the raw data, which was provided to me, that's the wrong one. There it is. The raw data was provided to me in the file labeled rent in our Canvas page in the section for the Chapter 8 downloads. There are those monthly rents. I copy that over, or I do it right here, and I say, I want the average of those numbers. So these 12 people had an average rent of $1,813. And then I want the standard deviation. But this is a sample, so I make sure it's .s. Same set of numbers. And now I can use my t-values. Equals t dot inv dot 2t. As soon as I hit the parenthesis, it gives me the prompt underneath that box. The first word it says is probability. What was my confidence interval here? 99% this time. So I'm going to need 0.1 on the outside, right? I'll use 0.1 in Excel, sorry, 0.01 in Excel, and then my degrees of freedom. Now I can add and subtract once I compute. So, equals average minus t-value times standard deviation divided by the square root of how many people there are. And then I do the same thing with a plus sign. And that gives me both ends. Helps if you actually make the formulas different. If you write the same formula twice, you're going to get the same value twice. There's my low end, there's my high end. Questions? Yeah.
Is there like a way I could like put the numbers in L1 and take the average out of the two?
Yes, you absolutely can do all of these same calculations in the statistics on the calculator. Average and standard deviation come out of our stats, one variable statistics. You can't see the calculator at the moment because I'm still sharing this thing. There, one variable statistics. So if you put your information in a list here, where we edit our lists, you can put in your numbers, and then you can do those calculations on here. It won't automatically do the t interval, I think. No, I do think. Yes. See down here at the bottom? It says interval. Under z interval, there's a t interval. I did tell you there was a sneaky part. I'm going to give it the statistics. The average was 1813. The standard deviation was, I got to go back and look at the Excel again, 3.106. And the number of people was 12. This time my confidence interval is 99%. All right, what did I screw up? 1810, 1815. This is what I get for not having done this in advance. Oh, I put in the wrong number. That's what I did wrong. Go back and look at the Excel sheet. What did I put in? For S, I put in the wrong number. In S, the standard deviation is 78.4, but I typed in 3.106. That's the t value. I put the wrong number in the wrong spot. This should be 78.4. That's much better. 1743 to 1833. Those are the same numbers we got out of Excel. I can also, as was mentioned in the data analytics course, I can also do this with a command called confidence. There is a command called confidence.t that will do the t times the standard deviation divided by the number square root in one step. It'll do the margin of error part. Confidence dot t of .01, comma, standard deviation, comma, size. That's the give or take. And if you take 18.13 and subtract 70, you get 1743. It's rounding off, isn't it? And if you add 1813 plus 70, you get 1883. That's the plus or minus in one step. I like that, because that would prevent me from screwing up dividing by the wrong thing. So confidence.t. Question. I would point out to you in addition that I can ask Excel for a bunch of descriptive statistics, right? We did that back in chapter 4. So if I asked Excel, hey, do all the descriptive statistics for this set of data, that's under my data tab, data analysis, descriptive statistics. Click. Where are your descriptive statistics? I want them right here. And they're grouped in a column, and I'm going to put it in a new pile. That's why the box that says new ply is checked. But notice underneath that there are a bunch of other boxes. Kind of hard to see on my screen, but you should do this on yours. The bottom boxes include something that says summary statistics. And that summary statistics has a grayed out box next to it. If I check summary statistics, I can add a confidence level. Confidence level for mean, I wanted 99%, didn't I? If I check confidence level for mean, it'll do this calculation there also. There's that 70.3 confidence interval margin of error. It's sitting right there. That's the confidence.t command. It did it by default. This is a powerful tool I got sitting here. And there's my average, 1813. There's my standard deviation, 78.4. And there's my confidence interval. Questions? So now I have two different versions of a confidence interval based on an average and what I know about my standard deviation. Yes? If I know something about the population standard deviation, I can use z-scores. If I know something about the sample standard deviation and not the population standard deviation, I'm going to use t-scores. But I don't always just measure averages. Routinely, I look at things like proportions. So I would go and I would gather some data and I would say 35% of people prefer soda X over soda Y. But if I think about it as a yes/no question, do you like this more than this? Yes or no? Then anybody who answered A over B, I get a 1. Yes, you like that more. If they answer B over A, I get a 0. No, you don't like that more. And that means that this population proportion is a mean for a bunch of numbers that are either 0 or 1. It's not a whole bunch of different numbers. All the numbers are either a 0 or a 1. Yes, I like the first one more, or no, I don't. Yes, I prefer candidate A. No, I prefer candidate B. Or swap them around, it doesn't matter. But the distribution is going to look like a number between 0 and 1. As my sample size increases, the central limit theorem tells me that this looks more and more like a normal distribution. So all of my ideas about sampling distribution still hold here. This is a consistent estimator. It's unbiased. It's a useful estimator, and it gives me what looks like a normal behavior. And that means that I can use the central limit theorem again. And that means that as I have more and more people in my sample, I get what looks like a normal distribution. Normal distributions have a mean and a standard deviation, right? The mean is going to be whatever that population mean is. But I don't know what the standard deviation is here. And I don't have a good way of calculating it in advance of my working with the data. But we were able to figure out a standard distribution for a binomial, right? That should be on the formula sheet y'all gave me, so I'll give them back to you and you'll get them from there. But if I go back and I look at my binomial distribution, and we think about what happens with our sampling distribution as it's getting more and more and more normal, this looks like a freaking binomial, doesn't it? And that means I can use what we were using as a standard deviation from the binomials. And in this case, that gives me a really nice, easy calculation. The standard deviation is P times 1 minus P over N under a square root. This is going to be called sigma P. That's my standard error. for a proportion. And that means as my n value gets bigger, I can actually use this as a normal distribution. If I'm using it as a normal distribution, that means I get to use z-scores instead of t's. Now, interestingly enough, it is really the size of my binomial ideas. When we were dealing with binomials, we had successes and failures, right? People checking bags. What was the exam question? Was something about ordering beer, right? That's they order a light beer or not? I think was the exam question. If I want to do this right, I need to make sure I have a sufficiently large number of successes and a sufficiently large number of failures to assume that I actually do have a normal distribution. And the number that's good enough, and this is a rule of thumb, we kind of made it up. We're trading off practicality and expense. I need at least 10 in each category. So I need at least 10 people in the group that said yes, and at least 10 people in the group that said no. If I write my proportion as x over n, I really need x to be at least 10 and n minus x to be at least 10. So the number of people I need to do that now depends on what I think the actual proportion is. If I was flipping a coin, then this would be 50%, wouldn't it? 50% is a half, right? So I need at least 10 people up here. So if I had exactly 10, then I would have to have 20 down here to get a half, wouldn't I? And that would mean that this would be 10 and this would be 10. 10 heads and 10 tails gives me 20. As the proportion gets further and further away from 1/2, the number of people I need in my sample to assume that I have a normal population gets bigger and bigger and bigger. Page 294, we have a table. If I think that the chance of success, that was the way we thought of our binomials, the chance of success, the chance of failure, is 30%, then I'm going to need at least 33 people, right? 11 successes would be 1/3, right? That would be bigger than 10. If I have only a 10% chance of success, I'm going to need 100 people to guarantee myself at least 10 successes, right? And we can see as these numbers get smaller in either direction, if I have a 10% chance of success, a 90% chance of failure. But I can do it the other way around. If I have a 90% chance of success, and a 10% chance of failure, I'm still going to need 100 people, regardless of which way it goes. I need more and more samples as my proportion gets smaller and smaller, whether that's the proportion of success or proportion of failure. If I don't have enough samples, there are other numerical methods by which I can use the binomial to approximate my normal distribution. This is a pain in the ass in Excel. There are other methods called bootstrapping ideas. Dr. Burns will talk about that a little bit, the quant decision-making methods. We talk about it more in the more general advanced statistics courses. If it's really too small of a sample, probably don't want to use this method. But now that I have this idea, if I have a large enough sample size, if I really do have a known standard deviation, therefore a known standard error, I can do a confidence interval for a proportion rather than a mean. And the advantage to that is that I take the proportion I got from my sample and I build that margin of error. The margin of error this time uses a z-score, not a t-score. Because I've got my normal behavior. And then I multiply by my standard error. You'll notice this time I used p instead of pi. Because this is the idea that I'm working with the information from my sample. Again, if I want a narrower margin of a narrower confidence interval, I either need to increase the size of my sample, thus making this fraction smaller, or I need to be willing to be less confident. And that'll make this value smaller. So here's the general idea. If I'm dealing with an average, I need to know what I know about standard deviation. If I'm dealing with a proportion, I don't care. My assumption is that it's normal. I'm going to use the z-tables. There. Question. It is possible to use this backwards. I don't know if those of you that were here at the beginning of class were hearing me talk to the gentleman who's in this room before us. He teaches Comp and Culture Part B, and he was talking about survey questions. And he said, but I don't know enough of the statistics to talk to them about sample size and margin of error and all the rest of it. And I said, that happens to be what we're talking about today. If I know the confidence I want, I can use that to figure out the sample size. So let's suppose for a moment that I think about this margin of error here. You see this in surveys all the time. We came up with this value plus or minus 5%, plus or minus 3%, plus or minus 2%. They're giving you the margin of error. They're giving you this output based on the sample size. So if I say we're going to do a 95% confidence interval, then my z value, what's the z value that goes with 95%? That's 2.5% at the top, 2.5% at the bottom. You had this number on your tables. Some of you had it on your formula sheet written down separately. We wrote this down last week.
Is it
Hang on.
90%?
Say again?
Is it 90? Is it maybe 1.96?
1.96 to go with that. That's the one in the box, right? Yeah, okay. So that's 1.96. If I want to be 95% certain I've gotten the right thing, let's pick the lowest number for a proportion in terms of the number of people I'll need. If I assume it's a coin flip, then I would have 1.96 times square root of 0.5, And then 1 minus 0.5 is also 0.5 over n. Yes? If I tell you I want a particular margin of error, you could use that and solve for n, couldn't you? I could rearrange that. I could solve for n here. And I could say, oh, I got to take MOE and divide by 1.96. That'll give me the square root of 0.5 times 0.5 over n. So I got to square. MOE squared, 1.96 squared. Hey, wait a minute, 0.5 times 0.5, that's also 0.5 squared over n. I got rid of the square root. But now I can just rearrange to get n all alone. And when I get n all alone, I get 0.5 squared, 1.96 squared over the margin of error squared. Notice everything in that entire fraction is squared. That means I can do the fraction first and then square. So if you tell me you want a 0.03, a 3% margin of error, I can tell you how big the sample size needs to be. And I can work this both ways. If you have a sample of 1,000 people, you'll get about a 3.5% margin of error. If you want a 3% margin of error, you need 1,120 people. Guess what? Every single election survey you see surveys 1,120 people, so they can announce it with a 3% margin of error. If you're surveying 1,200 people, your margin of error is 2.8%. So you know in advance, before you go out, if I want to be within 3% of the right answer, I got to ask 1,200 people. Making no other assumptions except to be confident enough. Now, there are lots of other sources of error in our possible surveys, right? There's bias, there's overcorrection for the diversity, there's sample, stratified sample, missing pieces. All the stuff we saw before talking about biases still exists. So it is possible that we'll get lots of other sources of error in our calculation. Question? There is a slight problem with my confidence interval when my proportion is really, really small. My proportion is really, really small, then when I do my confidence interval, I might get a negative number. The chance of this happening is negative 3%. Dude, what are you smoking? That doesn't make any sense at all. So if your proportion is really, really small, you have an artificial floor to your confidence interval. It really can't go below 0. So let's say you do this particular experiment and you don't get any successes at all. What happens? If your sample proportion is actually 0, you asked a survey and nobody said yes. You did an experiment and the thing you were trying to see happen didn't. Well, now I got a problem because my margin of error idea and my rules, they all break. Because everything in this formula was based on P. And if this is 0 and this is 0, then this whole thing is going to be 0. That means that this is a problem. And I don't have a good answer off the top of my head until I remember that a normal distribution, kind of like a binomial, right? And that means that all the stuff that happens way out there that is really unlikely is beyond 3 standard deviations. 3 standard deviations. I don't worry about the left side because if I'm at 0, all the left side is negative. I don't have to worry about the negatives. I have to worry about the top side. And the chance of that happening should be really small. No matter how many I've done, I should be 3 standard deviations. So we have this idea called the rule of 3. If in n independent trials, survey questions, etc., we have p equals 0, then a useful upper bound for my 95% confidence interval is 3 over n. I can think about being 3 standard deviations up. This is quite literally a hack. We estimated the normal distribution with the binomial. We then estimate the binomial distribution again. This is the result of a mathematician by the name of Poisson. Yes, this is a fish distribution. And he came up with this idea by approximating an approximation, but it works, and that's stunning. Question. There's a key word in this sentence that's going to come back and bite me in the ass. Independent. I have to have a large enough population that my sample is independent. My population needs to be, we used this phrase back in chapters 1 and 2, effectively infinite. What does it mean to be effectively infinite for a population? Liam?
So it would be a very large population.
Right, but there was a comparison between the size of the population and the size of my sample.
It's like a little n over big N, it's less than or equal to 0.5.
Little n over big N, the size of my sample over the population should only be about 5%. If I don't have a big enough population, if that sample size is too big, I can't be sure of independence. Maybe when I went around and started asking people questions, I ended up asking the same person more than once. Maybe when I pulled something to look at it, I threw it back in the population, I looked at it again, or maybe I just kept it out of the population, I ran out before I got a big enough sample size. Oh crap. I need to figure out how to adjust based on a finite population. I'll do that on Monday. We'll see you all then. Have a wonderful week, everybody.